hello everyone. As Chris said, my name is Håvard, and I am a PhD student in Norway, but last year I was a PhD student here at the university, and I taught this course, taught it in Zoom, so it's exciting for me to see real students, and very happy if you are asking questions and along the way, just raise your hand or start speaking. That is great. So yeah, and I'm also part of the Digital Geography Lab together with Chris. And so enough about me, I guess. What we'll be doing today is going through 3 notebooks. There are 4 on the webpage and in the CSE environment, but I'll be going through 3 of them. So covering overlay analysis, and then going on to aggregating data, and lastly classifying and reclassifying data in different ways in using Python. So if we start here on the webpage, they're split up in, as I said, 4 different notebooks. The last one that I didn't mention is simplifying geometries. It's a very short notebook, just explaining how you can basically simplify geometries if you have that. Not needed for this week's exercises, so I'm not going through it, but after class, if you want to, you can go through it by yourselves. Quite straightforward and short notebook, that is. Okay, so yeah, again, if any questions or I need to slow down or speed up or repeat anything, just let me know. But I think we can get into it. So I'll jump over to Jupyter Lab in the lessons directory under lesson 4. And this is what we have to work with. And we'll start with the overlay analysis notebook. And I'll remove the folders there. Is it an okay size on the follow along? All right, good. So you might be familiar with the terms used when we talk about overlay analysis from before. Quite common GIS operation terms. So it's about how to, when we have different data layers, how we can combine them in different ways. And some of the terms might be overlapping, or you talked about last week, but within the overlay analysis frame, we talk about, in this case, we're going to do an intersection analysis. So having 2 different data frames, getting the result of the where those layers overlap each other. Other types are the union, where we get the result from both layers as one resulting layer, and then different kinds of difference analysis, where we cut out the parts that are overlapping, and either get everything from the 2 layers that are not overlapping, or just from one layer or another. Yeah. So in this notebook, we're gonna use the travel time matrix, which is a matrix developed at the Digital Geography Lab that covers the entire Helsinki metropolitan area. So it's a grid data set, so grid cells for the entire region, that contains travel times from each grid cell to every other grid cell in the data set. And originally, or the matrix consists of one file for each grid cell that represents the travel times from that cell to every other. But we will be using just one in this notebook, and then in the exercise you will be given more different files of the travel time matrix. But in this one we will only be using the one that starts at the railway station down in the city center, and contains then travel times for all the different other cells to the railway station. Yeah, so that's the one file we'll be using here, together with a polygon layer with the municipality borders of Helsinki. So we want to take the grid layer and combine it with the municipality layer using an intersection analysis. Okay, so as often we start with importing our path, so we can access our data, and this should be familiar with you. So running the path cell where all the data is stored, and then we'll import GeoPandas and read in those two files that we have and save them in two variable names. So in the grid variable, we will have our travel time, and then in the Helsinki variable, we have our municipality border. Yeah. So we get an error message, but that should be all fine. We don't need to look at that. So to start, we can plot out our layers to visually get an image of what they represent. So to do that, we can take our grid layer and plot that. Let's see. This keyboard is not mapped in the correct way, but see how it goes. Okay, we'll take our grid layer first and plot that. We can give it a face color to make it more clear afterwards. This is going to be interesting if this keyboard is not mapped. If you just give me 2 seconds, I will try to all right, let me see now if I have it ready. Not yet. How about now? Sorry about that. How about now? Yes, okay. So let's start with our plot of the grid cells. Let's do this in gray color, and I get a type error. Good start. So quickly, just plotting our grid layer. We see here the entire Helsinki metropolitan area, and as you can maybe see, the edges are rugged, so that is our grid cells that are squares. So let's try to plot our Helsinki layer on top of that. See, let's store this in a variable so we can plot on top of that as well. So we'll take our Helsinki layer and plot that on the same axis, and we can give it a edge color to see, so we can see the extent, and since it's just the border, we can remove the color inside to give it as none. So we only plot out only see the border of the Helsinki layer. Okay, so as we can see here, we have the municipality border that extends out to the sea, and then we have our grid cell in the background. So what we want to do is to kind of, in a way, cut out all the grid cells that are not within the Helsinki border, so that we can continue to work with just the grid cells in the municipality. Okay, so that is kind of our task here. So yeah, the travel time matrix has, as you can see, a lot of it covers the whole large area. So it consists of over 13,000 grid squares, and we want to kind of limit that to only our region of interest. So a good practice is to before we start
doing our analysis on the two layers to check their CRS, coordinate reference systems, of the two different layers, so that we know that we can work with them. So let's print out for our Helsinki layer the CRS object of that, and we see we get a EPSG code of 3067. But what we can do is to try to make sure that they match, that they are both exactly the same. And one way to do that is using assertions, which was briefly covered in GeoPython course, I think. So the way that we can do that is using the assert operator, and then taking our Helsinki CRS object, and then check if that is exactly the same as our grid cell CRS. So double equal signs, and then what we want to check it against, which is our grid CRS. And then we can print out a statement if this raises an assertion error, so that we get an error message. So we could say CRS differs between the layers. All right. So if we run this, then we will check if the CRS objects are the same. And since we don't get an error message, then that has run successfully, and they are the same. Okay. Good. Then we are ready to kind of start working with our two data sets and do an analysis between them. So what we want to do is within overlay analysis, we can use the different types that talked about in the beginning. So the one we'll be using here is the intersection the type of overlay analysis. They work in, like, the Python syntax is more or less the same for each, so no need to kind of cover it many times, but we'll start with we'll use the intersection here for how to do that. And it is more or less quite straightforward. We take we can start with our grid layer that we have, and to do an overlay analysis, we use the overlay method. And within the parentheses, we check, or we provided the other data frame that we want to do the intersection against. So that will be our Helsinki data. And then, importantly, to define if we're doing an intersection or union, we use what is called the how parameter. And then within quotation marks here, we pass it intersection. All right, and then let's store that data in a new variable. Let's call it intersection clarity. All right, so then when we run this, we are doing our first overlay analysis. So let's see now how our data looks. Based on that, we can do a quick plot of the, I can scroll up a bit, intersection data, and then plot it. Yeah, we can give it a color if we want that. We'll do a blue color to keep with that theme. All right. So what we see here is should resemble kind of the border of the Helsinki municipality that we had before, the general shape. But we can also see that, for instance, over here on the left side, we can see some clipping of the grid cells. So the intersection analysis clips every feature along the edge that we intersect along. So some of the cells might be smaller than the initial cell, but we have gotten all the cells that are, or kind of all the area that is within those borders. Okay, is that understandable so far? It's the pace. How's the pace? Is it okay? Yep, super. All right, so now that we have done the intersection analysis, we can look at the data that is the result of that. So let's take our intersection data and just look at the head of that. So this is what the kind of what the travel time matrix looks like. We have
a bunch of columns along here. I'll get more into those later on, but they kind of describe the different travel modes and travel times and distances. Importantly here is from here it says from a specific cell to a specific cell. So here on the 2 ID is the ID of that cell that we are looking at. So the railway station in downtown Helsinki, and then each of the rows represent one cell in the rest of the data. All right. Yeah. So if we wanted, we could also get a new code cell here. We could see if we wanted to see how much our data has been reduced. We could print out the length of our grid data and run that. We get 13,231 rows. That was our initial data set. And then if we also print out the length of the intersection data set, we can see we are left with 3,800 cells. So it has clipped out a lot of our data to only the area of interest. All right. So yeah, the last thing we can do is to save our file if we wanted to work on that further. So we could take our intersection and save it to file in a way that you've probably done before, and using our data directory. Let's just store it straight there. We can just store it as a intersection .geo package, and then got a comma there. As saving it to a geo package, we can specify the layer name as well. So we can save it as a travel time matrix Helsinki region, and save that. Yes. Okay. So that is more or less how to do an overlay analysis in Python. Any questions so far? All clear and good. All right. Yeah. So when the syntax for the different types of operations is more or less the same. You swap out the how parameter here for if you wanted to do a union, you could get all the data from both data sets, which doesn't make sense with these two layers, but I think you get the point. All right. So if there are no other questions, then I think we can move on. So
I have one question.
Yeah, super.
Can you do like the same we did with the intersection, but it wouldn't like cut the like edge cells? They would like keep it as a whole, like squares.
I'm not. I don't think so. I don't think there might be some. You could check out the documentation for the overlay method if there are any options to do that. But I think that's at least the default way of how it works. I think that's more or less it. Yeah. All right. But so the next notebook that we'll go through is the vector data aggregating notebook. So is it clear for you what like aggregation means as a term, more or less? So taking data from one level, going up, often kind of summarizing the attributes. So having, say, if you have the average age for all the different municipalities in Finland, if you aggregate that up to a country level, you get the average of all those averages as well, and get one final average for the entire data. And that is an often common processing step that we do in GIS analysis. So we will do this again using our travel time data. Yeah. Again, start by getting our file paths in order and reading in our intersection data that we have. So let's just, for good practice sake, take a look at our data, see that it's what we would expect. And so what we will be doing here is doing our aggregation based on one of the different columns. The column named car_r_t, which is the travel time matrix has on the different columns. First, the mode of transport, so either car or PT, public transport, or walk for walking. And then has it in both distance and travel time, and also for the morning hours and during peak rush hour is when those times are calculated. Okay, so we will be using for this example, using the car in rush hour and T for travel time. Yes. So when we want to aggregate the data, the method that we use in here is the dissolve method. Similar to the overlay analysis, it's quite straightforward that we have our data set that we want to use, so our intersection layer, and use the method dissolve. And then the keyword that we pass to that method is by which column in our data that we want to dissolve by. So the keyword is by, and then we provide it with the column name that we want to use. And for our case, we will take the car_r_t and save that in a variable called dissolved. Right, and then let's just at the same time check out the head of our dissolved data to see what we're left with. Okay, so now we have printed out our table here that, as we can see, we have a new index, which is our the column that we chose. And in our travel time matrix, there are some values that are -1. Those are NA values, so we can disregard them when we continue to work. And then the 0 value is those here, the car rush hour travel time that takes 0 minutes from our starting point. And then we continue with all those grid cells that are 7 minutes away, 8 minutes away, and 9 minutes away. And we can see that our dissolve method has resulted in creating a new geometry that are some polygons and some multi-polygons, as some grid cells can be like equally far away but on different sides of the city center, for example. So that creates, but yeah, so they're still 8 minutes away, even if it's in Espoo or on the east side. So that creates a multi-polygon. Okay, so let's see, kind of look into the result, what we have to work with, how much have we are left in our data set, how many rows and geometries. So we can first print out the how much we started with in the intersection. Let's do an F string sake. So intersection length, and then in curly brackets do the length of our intersection, and then we can also do the same for our dissolved layer. So dissolved length and the length of dissolved. Right. So if we run that, we can see that we started with the 3,800 rows that we created in the last notebook, and we're left with 51 different rows in our dissolved data. And that makes sense since our polygons or different grid polygons are now merged based on the travel time. Okay, so we can also look at the different columns that we have in our dissolved geodata frame. So let's look at our columns and see that we have the same columns that we had before, except the or the column that we used as for aggregating. So that, as we can see here, that has been used as the index of our geodata frame instead. So if we look at our dissolved index, we can see here those numbers that should align with the index that we saw here. So we have from -1 our NA values, and then from 0 minutes ranging up to 56 minutes, about an hour of travel time. Okay. Sounds all right. So what we can then do with our data is to then go into, or by doing it this way, we can then access those grid cells, or those polygons that are exactly X amount of minutes away from our starting point. So let's do that by, we can take our dissolved data frame and locate the row that is 15 minutes away. As our index now is in minutes in a way, we can run this. We get a lot of deprecation warnings that are not really actually relevant to what we do, but yeah, so we still get the result underneath here that we get all the data for the row that is 15 minutes away. Yeah, so we can also take a look at what type of object this is. So if we take our dissolved, and again, the 15, we can see that we have returned a pandas series, which our data is stored in. All right. So far, so good. So we can then go on to try to visualize our data to see it more clearly. Skip that unnecessary cell. But in order to do that, we can what we can do it if we want to single out only the 15-minute grid squares or polygon, then we can take that as a selection, select that part of our geodata frame, and create a new data frame from this series object. So if we take our use geo pandas to create a new geodata frame, we can then pass it our pandas series that we just found. And the way we do that is to first pass it a list of all the objects that we want to use. Even though we just want to use one pandas series, we pass it as a list. But we take our dissolved data and again find the 15-minute row, and then good practice also define a CRS. Since that is not stored in our CRS or our pandas series, we can take the dissolved CRS and pass it in the CRS attribute. Yes, and that's also here, store this as we can use it, want to use it later as our selection of data. Okay. So now if we now take our selection just to look at it, we can see that we have a geodata frame that only contains one row of data. Right. So
let's try to see where those cells actually are, and then we can. And to do that, we can take our entire grid, the same way as we did earlier, define it to an axis, and plot out our grid cell, or our grid cells. Give that a color as well. Take that as gray, and then on top of that, take our selection and plot it with a different color so that we can distinguish those cells from the original, or from the original data set. So we take our selection and plot it, and let's do it to the same axis and give it a different face color. And let's call that, do it in red. Yes, we didn't have a grid layer here. We have the dissolved layer that contains all the grid cells. But yes, here. So plotting our dissolved first and then our selection, we can see we have a bunch of red grid cells that represent the 15-minute mark of travel time. And yeah, again here you can see why it is has dissolved it into multi-polygons. As we start off in the city center, then there are a lot of places around that are not necessarily in the same direction, but you can reach it the same amount of time. Okay. So, yeah, well, other way we could also kind of visualize all the travel times in that dissolved data frame that we have is to plot the entire data frame and then use the specific column that we want to use to visualize that. But since our dissolved layer has gotten a new index, and as we saw earlier, we don't have that. We don't have our car rush hour travel time in the columns. We want to kind of reset the index so that we restore our car RT column in our data. So the way we do that is if we take our dissolved data and reset the index, and let's save that as dissolved as well, and then we can take a look at our dissolved head just to see how it looks now. So now we can see that we have a new index that is not related to the travel time itself. It is from 0 going upwards, and then we have our car column in the list of columns that we then can use to plot it by. So if we take this new dissolved layer and plot it, we can pass it the column parameter and define which column that we want to visualize by. So in the column parameter, we can take this, I'll just copy the name, and if we run that, then it plots the entire grid cell for the Helsinki region, and just automatically colorizes all the grid cells based on the column that we decided on. Okay. Any questions? Yes.
How would you make a management that you know what's color represents?
Yeah. So very good question, how to make a legend. And we will do that in the next notebook, because this is just like a quick visualization of the data, but it doesn't really make sense. It doesn't necessarily, it's not very explanatory when we look at it for how, what it does. So you could, I guess you could, if you pass it the legend parameter and pass it true, it would produce a legend as well. So in a way, that's also a quick way to do it and makes it more explanatory.
but in the next notebook we will also kind of reclassify this data so that we can that it makes easier to read the map immediately. But yeah, good question. Anything else? Okay. Well, then we can get into taking our data and then classifying it based on different schemes, and that is in another notebook called the Reclassifying Data notebook. So a natural next step is to take our data and break it up in different classes based on different parameters that we want to make the map easier to read, and also kind of to group the data in different groups that make sense depending on what the underlying data is. So an example would be the example here is if you are looking for a new house or a place to live, and you want to find the places that are both within a suitable distance but also at the suitable price. You can take different criteria, those two as criteria, and classify the data into something that suits both, so that you find the areas or places that are within the correct travel time and also kind of budget as well. But for our purpose here, we don't have like the apartment prices, but we will use the travel time and the distance as two criteria to classify our data into. Yes, and there are many different classification schemes that serve different purposes, and we will be using the map classify library from the PySal library that contains a lot of different classification schemes that you might be familiar with from like ArcGIS or QGIS. There are different options there as well. These are the same options, but yeah, in Python. And then lastly, we'll also kind of create our own classifier and then try to apply that to our data frame to see how that works. Okay. So the two kind of criteria that we will be using is public transport travel time from the city center, and then also the distance as well. So again, we will be reading in our data path and then reading in our travel time matrix data, this time for the whole Helsinki region. Yes. So yeah, reading in our accessibility grid, as we call it here, our travel time matrix, again containing all the different columns for the different types and modes and time of day. And we can start to work with that data again. But yeah. Again, on like classification schemes, there are a lot of different schemes that have different purposes, and will split the data into different classes and groups based on how they work. We'll be looking into a few of those here, and some are more common than others. Yeah, and you'll probably be familiar with some of them as well. Yeah, so some of the most common natural breaks that we'll try to break our data into natural breaking points, and also the equal interval to get the same amount of interval between the different breaking points, and percentiles and quantiles, and that splits into a specific amount of classes. Okay, so we'll use the column in our data set that is called PT_R_TT, so public transport in the rush hour and travel time, and then we'll also be using the walk_D as the distance, the network distance
by walking. Okay. So as we saw, or in the last notebook, there are some grid cells that are have no data values, represented as -1, which we don't need. So the first thing we can do is to remove those from our data set. So we will subset the initial accessibility grid. I will also complete that because we will be typing it a bunch of times. But so we take our accessibility grid and use the lock method to locate those rows that are in our accessibility grid. And then in our, we will be using the public transport public transport column, which is pt_r_pt, and then only be looking at values that are greater than or equal to 0. And so in that sense, we keep all the values where we can reach by public transport, either by 0 minutes or more than that. And let's store that in, just replace the accessibility grid layer with our selection. Okay. So now we can also see if we put the length of the accessibility grid, we have dropped just the one, or just a few rows that are the NA value rows. So still, we have almost our entire data set. Okay, so let's start by plotting the data, and we can do that using the plot function that we are used to. But we will be here providing 2 new parameters and options. So the C map, which is the color map that we want to use, and then there's also a scheme option that defines which of the classification schemes that we use. So we can start with taking our first defining which column that we want to use, just like we did in the last notebook. So here we can take the public transport rush hour travel time, and if we run that, we will see the same type of plot that we had before. So just automatically colors all of the grid cells. But if we provided a scheme keyword, and then let's start with the natural breaks, with an underscore between the words, and if we run that, it will we will have a different looking map, because it then has split our data up where it has found natural breaking points in our data. And we can also use the K parameter for defining how many classes we want to have in our data, how many breakpoints, or how many classes. So if we provide it with 9, the result is slightly different, because we have limited the amount of classes, or either limited or expanded the amount of classes that we want to have, given it a specific amount. And then the last option we can do is also provide the color map that I want to use. And so here in the notebook, there's a link to the matplotlib library that is underlying with a link to the documentation of all the different color maps that are provided. You can read about all of them, but also there's a visual representation of how the color maps look, and also the kind of name or keyword that we can use to give it. So let's take a diverging color map here, and we can take the red, yellow, going from red to yellow to blue. So the shorthand here is like the first color, the next color, and the last color. So if we pass that in our CMap parameter, red, yellow, blue, and run that, we
should get a different looking map in a different color scheme. Right. And then the different color schemes, as you saw, there are a bunch of different that also have their different use cases, and some are more suitable for some use cases than others. So there's not a definitive answer to which is the correct in every use, but here we will be using the red, yellow, blue color map. Okay. So, yeah. So as we can see here, what our data look like, from the red is the areas that have low travel time values. Reaching out further out changes to blue color. Okay, so in a sense, the red color here represents kind of good accessibility, where the travel time is low. So what we can do is to also get a visual kind of image of what the case is for the walking distance. Yeah, to save some typing, we can copy the plotting from above, and then changing out the column that we're using. So instead of public transport, we can use the walking distance. So if we plot that, we should get a map that is much that still classifies the data in a similar fashion. So red, close to the city center, and then further out it changes to blue. Yeah, and as you can see, kind of the walking distance along the network in this case it resembles kind of Euclidean distance, as we have kind of circle pattern here. But yeah, this is how our kind of quick classification of when we are plotting as well. But then there's also a different option when classifying the data, to also, if we want to kind of work further with the classification, there's also ways that we store that classification data to either in the data frame, which we will do, or kind of get another image of the data and store the classification so that we can, for example, plot a histogram of the data. And to do that, we will be applying some classifiers to our data instead of just using it in a way. Yeah, and we will continue to use the map classify library here. So let's import it first, and then try to classify our data in using the first natural breaks classification. So in order to do that, we will use the map classify library, and then the functions are named after the classification scheme. So if we then take the natural breaks as a method, and we pass that the data that we have in the y parameter, it's called in map classify. So if we here want to look at one of the columns or one series from our accessibility data frame, we can take our accessibility grid and only look at let's start with our public transport rush hour time, and we can again define the number of classes we want to split it into, and then it quickly produces the classification that we have. And the information that we get here as well is the interval of the different classes. So how it has split it up so in this case from 0 minutes to 28 is the first class, and then next is 28 to 40, and we get that information as well as the number of grid cells in our case here that are stored in each, or that are in each interval. Right. Did that make sense? Like mostly? So we can do the same with our or with another classification scheme. So we can do it in the same manner. Map classify, and then use here we can take the quantiles classification, which classifies the data into 5 different classes, and again pass it our accessibility grid and the column that we want to use. So we take the public transport, rush hour, travel time. So yeah, in the quantiles classification, we can see we have different set of intervals that it splits our data into, and then it kind of tries to classify our data into equally sized groups, more or less. So classes are 2,500 grid cells in each. And if we wanted to do it, we could also do it for a different column in our data. So our walking distance column, here we only removed the cells in the public transport column that were -1. So here we have -1 in walking distance as well. But here you can see it has split our data into exactly equal sized classes, for example. Okay.
What does the count column shows, like 3 numbers of?
So what the count column?
Yeah.
The count column is then the amount of grid cells in each of those classes that it found. Yeah. All right. And so there are, as we see, there are 2 useful information here. It's the count number, and then it's the interval number as well. That we can access and use further as well. So yeah, if we take the natural breaks, I'll copy from the classification that we did up here. If we take our classification here and store it in a classification variable and run that, it is stored in a variable, and we can print out the type of the classification and see that it's a map classifiers classification, and the nice thing about that is that it has other built-in methods or attributes that we can access. So for example, if we wanted to access the threshold values or the breaking points of these, we could then access the bins attribute and get an array of the different breaking points. So here, 27, 39, if we scroll back up here, it counts it not with 0 indexing, so the numbers are like 27, which here it's included 28 in a way, or it goes from 0 to up to, but not including 28 here, and then from 28 up to, but not including 40. So the breakpoints are these, so 27, 39, 51. So kind of one less. But yeah, so this is the way we can access the different bins in our data. Yeah. Okay. Yeah, so that's how we kind of we have taken our data frame and then applied a classifier on that. Or no, we have not applied it. That's what we're going to do now. Yeah, of course.
Do you have an idea why I get different breaking points?
No, me too.
Okay.
Okay.
For
first is 30, then 42, 53. For the exact same function you have.
Okay, and also with the K9 break.
K
point.
equals 9, yeah.
Okay. No, I don't have an explanation for that.
You
That
can step over a few. 30, 41, 50, 61.
okay.
43, 54, 65.
Not really 40 or 50.
Okay. Yeah. I also get different if I run it again. Then I get 30, 43, 31, 43. So, and I think that's the natural breaks classifier can work in different, or it can kind of find different different breaking points because it tries to find kind of a natural breaking point, and that can vary. So had we used a different classification scheme, then we would get the exact same result in each. But I'm not entirely sure why it varies that much. But I guess that is like one of the caveats of using the natural breaks classification opposed to different. So had we used it with the quantiles, for example, then I'm pretty sure we would get the same result every time we run it, for example, because that is, yeah, it's not that variable. But excellent question. Okay. Yeah. So I think we can, or we're taking, we can, another way of creating a classifier and then apply it to our data frame in order to kind of store it for later use, is to first create the classifier that we want to use. So here we can do it in a similar fashion. So we, in our map classify library, we use the natural breaks method and use the make function to kind of initialize a classifier that we later on can apply to a data frame. And here again, we need the number of classes. Then we need to store it in a variable that we can kind of apply to our data. So if we store it in a classifier, and we can store that. We can also print the type of the classifier to see that we have create a function. So we have a function, and I think you might have been talked briefly about that in an earlier lesson on how to apply a function to a data frame, but that's what we were going to do now. Sorry. So if we wanted to kind of take that function that we created, apply it to a data frame, we can get the result and continue to work with that. So let's take our accessibility grid, and again select only a column, and in this instance we will subset the data passing it a list of the columns that we want to use. So we can take our public transport rush hour travel time, and then using the apply function or method in GeoPandas, we can apply a specific function that we have. So, and as we saw, our classifier that we just created is a function classifier. So if we run that, we can see that we get a what looks like either a data frame or a series here of the index that we keep with. We have 13,020 rows, which is the same number or the length of our accessibility grid, and then in this column that is now here, PTR_TT is the classification value that each of the cells are classified into. Did that make sense? So if we said we have 9 classes, so those numbers will be going from up to 8 is the 0 index, so 8 is the largest. But let's store this in a variable. Let's call it classifications.
And if we then call the head again, it will look similar. We can also even inspect the both minimum values, which is 0, and then max values to see that we 8. So the values here now range from 0 to 8. All right, and we can check the type of our classifications data that is stored in a data frame. Okay, so that means we have a data frame with our input column. Let me just take this to head again to make it clearer. So the index here, and then the different classes that our data is classified into, based on the natural breaks classification. Okay, so if we wanted to take that classification number or values and store it in our data frame, we can also do that to use later on. So if we want to create in our accessibility grid, create a new column, we can call it natural breaks or NB. Let's just call it natural breaks. Natural breaks. What we can then do is to, in the same way that we did up here, take our accessibility grid and the columns that we want to use, so the public transport, rush hour, travel times, and then apply the classifier that we had. Yeah, and then we can, if we do that, it runs, and we should have a new column in our accessibility grid data frame that is quite many columns. So let's just look at the public transport, rush hour, travel time, and the new column that we created, natural breaks, and see that we now have both the information of the travel time and also which class that that row belongs to. And now I remember why last time I called it travel time here as well, or public transport, because if we wanted to do this classification for a different column, we could kind of apply this classifier on a different column here. And so say we wanted to take another line here and say natural breaks for walking distance, and use the walk D here as well. We could do that and have a natural breaks walk D, and have the two different classifications stored in the same data frame alongside each other as well. So this way we could quickly kind of apply that classifier that we created to the same data frame, just using different columns as input. Yeah. Okay. Did that make sense? Okay, good. Okay, so if we wanted to then take a look at those columns, we can take our accessibility grid, or to see the classification rather, and plot it. And then again, using the column keyword here, we can now, instead of or use our classification natural breaks column, and let's get a legend as well, pass it true, and see how that looks. All right, so then we have the same result as before, but we've done it in another way, as it gives us more options to working with that classification data that we created. Okay, so now I'll move on to still using that classification data, but to visualize it in a different way. So using a histogram, which is a common way to kind of get more information about our classification data, not just in the text format that we saw up here, but get a visual impression of how our data looks, how it has been classified, how large are the groups, and then, where the breaking points are in our data set. Yeah, and it's often nice to, many times you can also kind of create a plot of the map on one side and then the histogram next to it to kind of get a more complete picture of the data and what it represents. Okay, so let's start with making a quick histogram of our accessibility grid. But let's use the only one column, keep it with the public transport rush hour travel time column, and use the built-in plot function as well. But instead of just calling that function, we can then use the underlying function, which is hist. And if we run that, we get a histogram of our data. So as you can see here, we have kind of our data plotted out in the frequency that the values are, but they are in quite kind of large chunks, quite large groups. So we could here specify how many bins, as it's called, we want to have. So if we have like 50 bins, it will split it up in 50 groups instead, and we can see a more granular view of how our data in the public transport data frame or column looks like. Okay, so we could do the same thing with our classified data as well. We will be using a small trick to kind of also plot out the different breaking points. As we here in our data, we don't see any break, or this is the public transport. But if we do it on the classified data instead, I'll just scroll up and get the classifier that we created here. No, okay, I will type it out instead, just to make sure that's right. But what we can do is to kind of first classify our data and then use that to plot out both the histogram of the different classes, but also the different breaking points. So like we did earlier, we'll make a classifier that we define from the map classify library. We can take natural breaks, and as earlier, provide the accessibility grid column that we want to use here. So we can continue with public transport rush hour travel times and the amount of bins that we want to use. So that is the classifier that we want to use, and then we can, as above, we can take our public transport column here to plot out a histogram of that, the same as above. So plot hist and give it 50 bins as well. And so far nothing new. We have the same as above, but as we saw earlier, when we have created a classifier like this, we can also access the different breaking points. So classifier.bins stores an array of the different values that we saw might vary in natural breaks, but here we have them. And one trick to kind of get the different breaking points is to loop over this list or array of values and then produce a line in our histogram. So if we take our classifier bins and turn it into a for loop,
So for each breakpoint in our classifier bins, so each of these values, we can use the matplotlib library. Above here we imported the pyplot as plt for shorthand. So plt, and then if we use the method with a weird name, axv line, so a vertical line on the axis, and if we do that for each of the breaking point values that we have, so for each breakpoint we do that, we create a line. If we run that, we'll get a breakpoint at each of those different, or a line for each of the breakpoints. We can give it another color to make it more clear. K for black, and we can use another line style. It's gonna have a dashed line instead to make it more clear. Well, that is a way to kind of see our different classes as well. So see how our data is both distributed and also how much of the data is in each of the different classes. Okay. Was that more or less clear? Okay, we'll do it one more time, but for using a different classifier to kind of see how that turns out. So I'll copy this so we don't have to type it by here. Use, instead of natural breaks, we will use the quantiles. Classifying scheme, which produces a resulting histogram with the different breakpoints. So then we can see which kind of how large the variation is within each of the different classes in our data. Okay. There is a check your understanding part, but I think for at the interest of time, I give that as an option that you can do later, and I will continue on how we can classify or apply a custom classifier again in our data set based on multiple criteria, as I talked about in the beginning of the notebook. If we have kind of not just want to see the range in the data, but if we have different criteria and we want to classify the data using those, we can do that as well. So the way that we are going to do that is that we have our travel times and our travel distances in our geodata frame, and we will check for all the cells which are within a suitable length or like distance and a suitable travel time to get to from the railway station. So in order to do that, we will check either if it meets those criteria or if it doesn't. So we have like two different outcomes, and that's what we call like a binary classification, or also Boolean output values. Okay, so we will use those two criteria, and then we will take a lambda function and apply that to our geodata frame. And I'll get back to lambda functions, but it has also been introduced, at least as a hint to one of the exercises earlier. But it's a handy way to apply a quick function to a data frame. Okay, but let's first see how we can kind of check whether or not our rows in our data are both less than 20 minutes away by public transport and less than 4 kilometers away. Okay, so in order to do that, we can first, if we take our accessibility grid, and let's just start by looking at like the first row to see how to build up this criteria. So we'll take our first row of data, and also the column that we're interested in. So let's start with public transport in the rush hour again, and see if we say if that is less than 20 minutes, we will get a false value. So here we check if the value in the first column, or first row in the public transport column is if the value is 20 or less, or if it's less than 20. And the output that we get is a false. So that is, let's see, now I'm freeballing a little bit, but we get, the type of that is a bool or Boolean value. So Boolean values are binary values. They can be either true or false. So that is handy to remember. Okay, so that is just our first condition. So if we have another condition, we want it to be both less than 20 minutes away, but also, so and is the keyword here, and also less than 4 kilometers away. So I will also, again, copy this. So if we take, again, our accessibility grid, the first row, but then look at our walking distance column, and see that it is, let me see here. Yeah, and okay, our parameters as described here are that they are both lower than 20 minutes away, but more than 4 kilometers away. So let's check that our the value in the walking distance is more than 4,000 as well. So now it again produces a Boolean value, or a Boolean value, true or false, but it has to kind of meet both of those criteria. Let's just, for interest's sake, see if we only look at the distance. It is more than 4,000 meters away, but since we also wanted it to be less than 20 minutes away, then it results in false. Okay, so so that's kind of our two criteria and how we want to kind of check that. But a handy thing to also know is that if you have Boolean values, true or false, if we want to kind of convert that into a number, we can do that quite easily. So if we take convert the whole Boolean value into an integer, it will be either 0 for false or 1 for true. So if we just did it again for the walking distance that we know was true, then it results in 1. Okay? Did it make sense? Yeah. Okay, so and I can do the same way. If we run that cell again, it was false, and I'll copy it, and I have checked one specific other cell just to see that we can also get other results. So we can, if they are both true, then it results in 1. So here I just looked at a different index in our data frame that happens to be both less than 20 minutes and less than or more than 4,000 meters away. Okay, so now we kind of have our we know how to figure out if a row meets our criteria, and now let's apply that to our data frame. So the way we can do that is to take our accessibility grid, and then we will apply a lambda function. So we use that, take it, apply, and the lambda function is kind of an anonymous function. We don't give it a name, and we just use it here. We don't store it for later use, but we use it here just once. But it's a quick way to, you don't have to kind of define a function, store it in memory, and all that, if you're just using it for this one case. So what we could do is to kind of iterate over each row in our data set, but that is a slow way of doing it, especially with larger data sets. But a lambda function works quicker.
So what the lambda function, how it works is that we use the keyword lambda that we apply, and then a temporary kind of variable name for what the data it gets when it reads a row. Here we just call it row. And what we then want to do is, now it looks at the whole data frame, but we would just want the wanted to look at the or we wanted then to pass it the kind of this long sentence for how we want to classify our data or the conditions that we have. So if we take this, but instead of reading in the accessibility grid, the whole, we want to read in the row that it uses. Does that make sense, or was it too quick? Okay, so our lambda function reads in the row, and for each row we only okay, I copied the wrong thing here. Let me do it properly then. Okay, so we want to take our row and then look in the public transport column. That is our first condition here. That was supposed to be less than 20 minutes. But also, in each row we want to look at the walking distance. That we define as being above 4,000. And then we want to store it as a number instead of the true false. So we take the whole condition that we have and convert it into a number, an integer. And then for the lambda function to work properly on row based instead of for the whole data, we pass it the axis. So which axis it will use, and it will use the axis 1. So then it takes for each row sideways in a way. Okay, so if we run that, we can see we produce a series with the index here and all the integer values of either 0 or 1. Okay, so what we want to do is to store that in our data frame in a new column. So we take our accessibility grid and create a new column, and let's call it suitable area. So that will store which of the grid cells are suitable for our criteria. So if we run that, that should be stored in our accessibility grid. We'll take a look at the head here, which is long, but we will see that the last column we now have is this suitable area column. Right. And so one of the advantages of doing it in that way is that we now can quickly look through our whole data set or data frame to, for example, see how many of the rows were classified as suitable area. So one way to do that is to take our accessibility grid column that we're interested in, so suitable area, and do the value counts function. Counts. Then we get all here is for the suitable area, the two values that they can have, 0 and 1. And so 13,000 rows have the 0 value, and only 9 rows have the 1 value. So 9 of the grid cells should be suitable locations for us. And then the last thing we can do is to try to figure out where they are. So we can plot out the accessibility grid, and then passing only the column suitable area. Suitable area. Yeah, let's just keep it simple. Which should produce a map, which might not be the most easily readable map, but we see here that we have most of the cells as one color and just a few cells in a different color. So all the purple cells here for the
0 values, so not suitable, and the yellow dots are the 9 grid cells that we classified as suitable areas. All right. Any questions? Okay, so everything was clear. Good. Then I think we can start to land this lesson. Can briefly introduce the exercises for this week. So on the web page, if we go to the GitHub for the exercise 4, there are 2 problems split up in 2 notebooks for you. So in the first notebook, the first problem is to join accessibility datasets into a grid. So you will be in the data folder. There are now different text files for different of the travel time matrix. So the travel time to different cells. In the notebooks today, we just used the railway station, but here there are 2 different shopping centers in Helsinki. So you will be visualizing the travel times to the different shopping centers by different transportation means, and kind of the end result producing a grid plot where you can compare those maps. Yeah. So you will be reading in data and joining the travel times to the grid cells, and then classifying the data and plotting it in different ways. And then the last problem is to kind of calculate and visualize the so-called dominance area of the shopping centers. So which shopping center is closest by different travel times. So yeah, the different travel times to the different shopping centers, and then combining it on one map based on what is the closest one. So in this exercise, it's kind of all the information is at the top and all the instructions, and then there's a bunch of code cells that you can kind of do it in the way that you want, as long as the kind of output name is what we are provided here. But you can do it in the way that you want, and you can add code cells if you want to. But all the instructions are kind of at the top, and then there's not one way to solve it. You can do it in different ways if you want to. Yes, I think that's it for the exercise 4. And then Chris informed me that the last 2 exercises, or exercise 1 and they are, the deadline for those have been extended to this Friday. So if you want more time to work on that, you can do that. Yes, I think that was more or less it. And yeah, there's one, as I said in the beginning, there's another notebook that you can go through on your own if you want to look more into how to simplify geometries and a way to do that. Okay. Yeah, and then there are some hints to the exercises for this week that are quite handy for you to read on how to kind of join the data based on different column names that you might want to use to join 2 different data sets together, and then also how you can rename the columns to after you have joined data sets. They might get not so meaningful names sometimes, depending on how you do it. So how to rename them for using later, and then also how to do it and how not to do it is also here. And so how to search for files, as you will be using different travel times to different shopping centers. A refresh on how to kind of search for files in a data directory. And then lastly, a handy way to find the minimum values across different columns in the data set. So if you have kind of joined different data sets together and you want to find the minimum values in multiple columns, then I would recommend to have a look in the hints section here for this week. Okay, then I would just say thanks for having me, and good luck with the exercise.